It is common to have to determine where lines on the ground intersect. Many data collection programs will calculate the intersection after entering the field information. The calculations where two lines intersect does combine many surveying calculations. An example of the surveying calculations will suffice to provide a broad overview of surveying calculations. In the example, the intersection of two sewer lines must be determined. The sewer line is old. The manhole at the intersection must not have been made with metal, or perhaps there was no manhole when the connection was made. The location of the sewer line intersection cannot be determined by a metal detector. Two manholes on each of the intersecting lines have been identified and located. These manholes are labeled 1 through 4. Manholes 1 and 2 are located on one sewer line. Manholes 3 and 4 were located on a second sewer line. To determine the intersection, the following steps were completed. First, traverse stations are established. Traverse stations provide a control network. When establishing traverse stations, particular attention is devoted to ensure there is visibility between consecutive traverse stations. Connecting lines between consecutive traverse stations should form a closed figure. A closed figure is used in order to provide a computational closure check on the measurements. From at least one traverse station, there has to be an unobstructed view of a manhole, or at least a prism set up over the manhole. For a check, the manhole should be observed from at least two traverse stations. Each traverse station is occupied sequentially. The surveying instrument is back-sighted and zeroed upon the previous traverse station. The interior angle and distance to the next traverse station is obtained by turning a clockwise angle and measuring the distance. It is important that the angles be measured with the instrument in the direct position and once again with the instrument in the reverse position. This will provide a check and eliminate instrument error. An angle and distance is measured to each manhole. The measurements from the traverse station to the manhole is known as a side shot. To obtain the side shot, the instrument is placed over a traverse station. A back sight and zero set is made to another traverse station. The clockwise angle is turned to the manhole and a distance is measured. It is important that the angle be measured with the instrument in the direct position and once again with the instrument in the reverse position. Given the large size of a typical manhole, high precision between the measurements is not likely. A logical question is to ask, why not just occupy the manhole rather than make a side shot to the manhole to obtain its position? The answer is traffic safety. To occupy the manhole would require a complete traffic road safety work zone display. On the other hand, an inexpensive reflector can be set over the manhole when simply walking across the street. In other situations where intersections must often be found, the position of the objects of interest could not be occupied by an instrument. Objects that could not be occupied by an instrument may be the corner of a building, utility pole, stone wall, fence, and so on. Unless CAD or coordinate geometry software is used, the computations will be done using a calculator and a worksheet or a spreadsheet. A computational sheet is used to keep track of the computations. A computational sheet that is used in this example will have the following headings: station, angles, adjusted angles, azimuth, distance, latitude, departure, x-coordinate, and y-coordinate. The traverse stations are listed in sequential order, with the first station listed again at the end. Following that listing, the side shot stations are listed beginning with the backside station, occupied station, and manhole. To avoid crowding the numbers on the worksheet, skip a row between the data entries. For each occupation, the average of the instrument's direct and reverse angles and distances are obtained. An example will suffice to show the method. The direct angle and distance for traverse station 1 is shown. The reverse angle and distance for traverse station 1 is shown. The average of the interior angle measured at traverse station 1, backsighting on traverse station 4, and turning a clockwise angle to traverse station 2 is obtained. Once this task is completed, the average angles and distances are placed into a spreadsheet or computational sheet for further calculations. The interior angles of the traverse are summed. the sum of the angles should equal the number of angles minus 2 times 180 degrees. In this case, with 4 angles, the interior angle should sum to 360 degrees. The angles sum to 8 seconds more than 360 degrees. The 8 seconds of excess is divided by the number of angles, in this case 4, to give a correction of minus 2 seconds for each angle. 2 seconds are subtracted from each angle to obtain the corrected angles. The sum of the corrected angles is checked against the number of angles in the traverse minus 2 times 180 degrees. The sum checks. A starting azimuth between traverse station 1 to traverse station 2 is obtained. The starting azimuth could be obtained from a compass reading, solar observation, or a guess. A guess would suffice. The basis of the azimuth is not critical in this situation. A starting azimuth of 83 degrees will be used based on a compass bearing. For interior angles going around the traverse counterclockwise, the next azimuth is found by calculating the back azimuth and adding the interior angle. The back azimuth from the occupied station to the backside station is determined by adding or subtracting 180 degrees. If the azimuth to the next station exceeds 360 degrees, 360 degrees is subtracted from the azimuth. These steps are repeated around the traverse until the starting azimuth is calculated again. The final azimuth calculated should equal the starting azimuth. The latitudes and departures are calculated. The latitude is equal to the cosine of the azimuth times the distance. The departure is equal to the sine of the azimuth times the distance. The latitudes and departures are calculated for each line of the traverse. The latitudes are summed. The departures are summed. Since the traverse is a closed figure, the sum for the latitude and the sum for the departures should equal 0. The sums do not equal 0. However, the error is so small that no adjustment is necessary. Keep in mind that the final calculated point of intersection, if within a couple of feet, is sufficient to locate where the sewer lines will intersect. Starting coordinates are assigned to traverse station 1. In this example, the x-coordinate is set to 2,000 feet and the y-coordinate is set to 2,000 feet. The starting coordinate should be large enough to avoid negative numbers. The departure between the stations is added to the x-coordinate to calculate the new x-coordinate. The next departure is added to the previously calculated x-coordinate to get the next x-coordinate. This procedure is repeated until the first x-coordinate is calculated at the end. There will be a difference between the starting and ending x-coordinates since there was a small error in the sum of the departures. The latitude between the stations is added to the y-coordinate to calculate the new y-coordinate. The next latitude is added to the previously calculated y-coordinate to get the next y-coordinate. This procedure is repeated until the first y-coordinate is calculated at the end. There will be a difference between the starting and ending y-coordinates since there was a small error in the sum of the latitudes. This completes the traverse calculations. The calculations for the side shots can now begin. Azimuths are calculated by obtaining the azimuth from the occupied traverse station to the backside traverse station and adding the angle observed at the traverse station that was measured to the manhole. Compare the calculated azimuth to the diagram to see if the azimuth that was calculated appears to be reasonable. The latitudes and departures from the occupied station to the manholes are calculated. The latitude is the cosine of the azimuth from the occupied station to the manhole times the distance from the occupied station to the manhole. The departure is the sine of the azimuth from the occupied station to the manhole times the distance from the occupied station to the manhole. The x and y coordinates for each manhole are calculated by taking the x coordinate for the occupied station and adding the departure, and taking the y coordinate for the occupied station and adding the latitude. This completes the coordinate calculations for all the side shots. The calculations for determining the intersection can now begin. The intersection of the two sewer lines is found by creating a triangle. The 3 points of the triangle are manhole 1, manhole 4, and the point of the sewer line intersection, that is sought. One side of the triangle is between manhole 1 and manhole 4. Another side of the triangle is a side extending from manhole 1 through manhole 2 to the point of intersection. The final side of the triangle is a side extending from manhole 4 through manhole 3 to the point of intersection. Solving for the azimuth and the sides of the triangle can now be performed. The difference between the x-coordinates and y-coordinates of the manholes are found by subtracting the forward coordinate from the back coordinate. Since the sewer line is going from manhole 1 to manhole 2, the coordinates for manhole 1 are subtracted from the coordinates for manhole 2. Similarly, since the sewer is going from manhole 4 to manhole 3, the coordinates for manhole 4 are subtracted from the coordinates for manhole 3. Finally, the side of the triangle from manhole 1 to manhole 4 must be found, so the coordinates for manhole 1 are subtracted from the coordinates for manhole 4. The azimuth from manhole 1 to manhole 2, and the azimuth from manhole 4 to manhole 3, and the azimuth from manhole 1 to manhole 4 must be calculated. The azimuths are calculated using the arctangent function and the table that is shown. The false azimuth is equal to the arctangent of the change in x divided by the change in y. The false azimuth will be a positive or negative number between 0 degrees and 90 degrees. If the change in x is positive and the change in y is positive, the azimuth is equal to the false azimuth. If the change in x is positive and the change in y is negative, the azimuth is equal to 180 degrees plus the false azimuth. The false azimuth will be a negative value. The remaining two possibilities are shown in the table. The triangle side distance from manhole 1 to manhole 4 is calculated. The distance is calculated by squaring the difference in x, squaring the difference in y, adding the difference squared together, and taking the square root. The interior angles are calculated by taking the difference between the azimuths that are emitting from a point on the triangle. The angle at manhole 1 is calculated by subtracting the azimuth from manhole 1 to manhole 2 from the azimuth from manhole 1 to manhole 4. Similarly, the angles at manhole 4 and the interior angle at the point of intersection are calculated. The three angles should sum to equal 180 degrees. The length of one side of the triangle between manhole 1 to manhole 4 has previously been calculated using the inverse formula. The remaining two sides of the triangle can be calculated using the law of sines. The length of the side of the triangle between manhole 1 to the intersection of the triangle is found by dividing the distance between manhole 1 to manhole 4 by the sine of the angle at the intersection multiplied by the sine of the angle at manhole 4. The length of the side of the triangle between manhole 4 to the intersection of the triangle is found by dividing the distance between manhole 1 to manhole 4 by the sine of the angle at the intersection multiplied by the sine of the angle at manhole 1. The x and y coordinates of the point of intersection can now be calculated. The x coordinate at the intersection is determined by taking the x coordinate for manhole 1 and adding the sine of the azimuth from manhole 1 to the intersection times the distance from manhole 1 to the intersection. The y coordinate at the intersection is determined by taking the y coordinate for manhole 1 and adding the cosine of the azimuth from manhole 1 to the intersection times the distance from manhole 1 to the intersection. A check on the coordinates of the point of intersection can now be done. The x-coordinate at the intersection can also be determined by taking the x-coordinate for manhole 4 and adding the sine of the azimuth from manhole 4 to the intersection times the distance from manhole 4 to the intersection. A check on the y-coordinate at the intersection is determined by taking the y-coordinate for manhole 4 and adding the cosine of the azimuth from manhole 4 to the intersection times the distance from manhole 4 to the intersection. The the x and y coordinates are the same. Next, the azimuth and distance from a traverse station to the point of intersection is calculated. The traverse station chosen must have visibility to the point of intersection. Of course, with a GPS receiver, the coordinates can be entered and the point of intersection located using the GPS receiver. The azimuth is calculated using the procedure to calculate the azimuth between manholes 1 and 2 or 4 and 3. The distance is calculated using the procedures to calculate the distance between manholes 1 and 4. Getting the difference between the azimuth from the occupied traverse station to the back site's traverse station and the azimuth from the traverse station to the point of intersection gives the clockwise angle that must be turned to locate the point of intersection. That completes the calculations. The angle and distance that were calculated can be taken to the field and the point of intersection located in the field. Many of the images used in this video were licensed from Shutterstock. The images are available from shutterstock.com.